Okay. Good morning, my student friends, all of you, and I thank the organizers for their help and encouragement in giving the classes. Even they came early, and they are with us. Thank you very much. And my student friends, yesterday we were discussing the fluid fundamental properties, and I have received, one query from one or two students. They want me to, to throw again light on surface tension. Okay, morning, and I will also give solution to the problems which I was given yesterday. And afterwards, I will be going to the objective questions and get questions for this chapter, and we will start the second chapter also. So, the surface tension issue. Yeah. So the surface tension is a simple concept. I will go a little slow. So let us say this is a free liquid surface. Free liquid surface. As you know, free liquid surface is the surface is exposed to atmosphere. As it is free, liquid surface free means it is exposed to atmosphere. FLS, it's a standard convention. And this is exposed to atmosphere pressure, and this is all fluid here. This is all fluid. Inside this is all fluid. I have considered two molecules, water molecules. This is all water here. So I have considered two molecules here. One molecule in the interior. Interior means the position is in the water body. Interior, liquid interior means the molecule at A is in the water body, below the liquid surface. So now I have considered one molecule here and one molecule exactly at the water and air interface here, exactly at the surface. And if you see here, so the fluid, this study is for fluid statics. That means fluid is at rest. In other words, fluid is in equilibrium. Fluid equilibrium means if fluid is at rest and the water molecule will not move this side or that side as the fluid is at rest. So this is a molecule at A, and normally you think that there will not be any single molecule. So the molecule will be surrounded, this molecule will be surrounded by a number of molecules, water molecules. These are all water molecules. These are all water molecules. You cannot get a single drop inside a water flow. Not a flow, water in a static condition. So this is a molecule at A which is surrounded by a number of molecules on it. There will not be any gap to the molecule at A which is surrounded by other molecules here. So as there are, so let's say this is a molecule here, we have molecules around this molecule. As this is a molecule here, we have the cohesion. The surface tension is due to cohesion. Cohesion means it is intermolecular attraction. Molecular attraction between molecule of same liquid. So molecule of liquid to molecule of liquid is cohesion. Cohesion is intermolecular attraction. So because of this intermolecular attraction, what happens here? The same molecule here and same molecule here, which is attraction between these two molecules here, and it is attracted in this direction here, attracted by other molecule in the other direction here, attracted by other molecule in the other direction. In other words, all the molecules surrounded by molecule A, it tries to attract each other. So then consequently what happens, if it is pulled all the directions, it will be in the same position. If it is pulled around all positions, the molecule at A will be in the same position. In other words, the molecule at A is in equilibrium. That means it is not moving, it is at rest condition because of the molecules around that, and it is equally attracted to all the sides and equally pulled to all the sides, and as the forces are all in all directions, the molecule at A is in equilibrium. Equilibrium means the fluid is at rest. The molecule at A is at rest. So this is the molecule in the liquid interior. Again, if you take the molecule at the surface. So this is the molecule at the surface. If you see here, we have molecules on all the sides. We have molecules on all the sides except on the top. Except on the top. So when there are no molecules on the top, what happens here? So this molecule will attracts this molecule, and here we have molecules here, here there are molecules here. Consequently, there is a net downward force on the molecule at this location. because there is no other force to counteract above. So it's supposed to be a net downward force. Net means the upward force minus downward force. Net downward force on the molecules which are at the surface. On the molecules which are at the surface. So because upward force here, there is no molecule above that. If you see here, we have no molecules on the above surface. We have molecules only below free liquid surface, and it is attracted towards all the sides. And as there is no other force which is counteracting, there is supposed to be net downward force on the molecules at the surface. But it is not also coming down. It is not coming down, and it is also in equilibrium. It is also in rest condition. The reason is surface tension. So surface tension, you can say that whatever the net downward force on the fluid at the surface, which will be counteracted by surface tension. So if you see here, this is more here, and this is the upward force, whatever it is. The upward force is due to the surface tension, which counteracts the net downward force. So the surface tension, we can say that it is defined as the force required to maintain the film, unit length of film in equilibrium at the surface. That's why it is called surface tension. Surface tension. It is at the surface. So normally we are giving the surface tension for air and water, for air and mercury, like that. That's why it is called surface tension. So surface tension. So as the molecules at the surface are not coming down, this is also an equilibrium. The reason is it is held in equilibrium because of the upward force due to surface tension. So the surface tension, now we can define the surface tension. It is the force required to maintain unit length of film in equilibrium at the surface. So I hope it is clear. And two to three students have again asked me for surface tension. Yeah, yesterday we have discussed some problems. I will give answers for that. So the first problem is he has asked to find out shear stress. So shear stress, Newton's equation of viscosity. Try to remember all these things, because the essence of this chapter is going to be advantageous. Is going to be easy for you to follow the other chapters. Fundamentals. So small u is the velocity distribution here. Small is the velocity, and y is the distance. U and y. Yesterday we had discussed it. Find out the shear stress at y is equal to 9. Viscosity has given 8 points. So you can find out du by dy. So because Newton's equation of viscosity, tau is equal to mu into du by dy. Mu is the dynamic viscosity or coefficient of viscosity or absolute viscosity. All the three refer to the same. So tau is equal to mu into du by dy. So du by dy is 1.5 minus 3 by 2. Y to the power of 3 by 2 minus 1. So this is square root y. So finally du by dy is 1.5 minus 3 by 2, y to the power of 1 by 2. So y is 9 centimeters here. So this is in CJ system. So convert in MK system. So when it is 9 centimeters, take y is equal to 0.09 in meters, 9 by 100. So here now it is 1.5 minus 3 by 2. And 0.9 to the power of 1 by 2. The answer is du by dy at y is equal to 0.9 meters is equal to 1.05. That is per second. The unit of du by dy is per second, because the velocity is meters per second and the distance is meters. So that is 1 by second. And mu is the dynamic viscosity. So you can convert this viscosity into MK system, and this divided by 98.1. So because 0.10, 1 Newton, Newton second by meter square is equal to 1 by 9.81 kg force seconds by meter square is equal to 10 points. So 1 kg force seconds by meter square is equal to, or in other words, 1 points is equal to 1 by 98.1. 1 by 98.1 kg force seconds by meter square. So you can straight away use 8 by 98.1 to convert poise into the MK system unit. So poise, as you know, it is 9 seconds per centimeter square. So you can convert poise into kg 4 seconds per meter square. So this is 8 by 98.1. So now the viscosity is 8 by 98.1. So that is coming around 0.0815. 0.0815 kg 4 seconds per meter square. And if you use tau is equal to mu to d by dy, so mu is equal to 0.0815 and d by dy is 1.05 and the answer is 0.0856 and the shear stress is kg force per meter square. So answer is 0.0856 kg force per meter square. That's the first problem solution. And second problem, can find out the kinematic viscosity when dynamic viscosity 8 points. Very simple problem. The relation, it is required to know the relation between kinematic viscosity and dynamic viscosity. So mu is equal to mu by rho. Kinematic viscosity kinematic viscosity means mu is equal to mu by rho, and kinematic viscosity is equal to dynamic viscosity by mass density. Mass density as well as a mass per volume. So mass density for water at 4 degrees centigrade is equal to 1000 kg per meter cube or 102 msl per meter cube or 1 gram per cc. Remember the conversion and the standard values. So now we have a kinematic viscosity is equal to mu by rho. First convert the dynamic viscosity into MK system. So that is 8 by 98.1. So 8 by 98.1 is 0.0815. 0.0815 kg 4 seconds by meter square. And the mass density in MK system is 102 metric slugs per meter cube. 102 metric slugs per meter cube. So the kinematic viscosity is equal to mu by rho. Mu is 0.0815 and rho is 102, and the kinematic viscosity is equal to 0.0079 meter square per second. And centimeter square per second is called Stokes. So this is the solution for problem 2. Only the relation is kinematic viscosity is equal to dynamic viscosity by mass density. So please remember the equations and also conversion of units from one system to other system. The other problem is 1 liter of crude oil weighs 0.96 kg force. Find out the specific mass density. So 1 liter is 1000 cc. 1000 ml. 1 liter means 1000 ml. 1 ml is equal to 1 centimeter cube. So 1 liter is equal to 1000 cc, which is equal to 1000 into 10 power minus 6 meter cube. So 1 liter is equal to 1000 into 10 power minus 6 meter cube. So that is volume. And we have the weight here, 0.96 kg force. So the specific weight is weight by volume. The specific weight is weight by volume. So weight is equal to 0.96. And the volume is equal to weight by volume. Volume is equal to 1000 into 10 power minus 6. So the specific weight is 960. The specific weight is 960 kg force per meter square. And mass density, we have relation between mass density and specific weight. Mass density, specific weight. Mass density is equal to specific weight by acceleration due to gravity. Mass density, which is equal to specific weight by acceleration due to gravity. Acceleration due to gravity is 9.81 meters per second square. So now the mass density is, so we have 960, the specific weight is 960, that divided by 9.81, acceleration due to gravity in meters per second square. So the total is 97.85 metric slugs per meter cube. 97.85 metric slugs per meter cube. Normally for water it is 102 msl per meter cube. For water, 102 msl per meter cube. For oil kerosene, it obviously the mass density is less because the specific gravity is less. Specific gravity of water is 1. Specific of the oil may be 0.8 or 0.9. In this case, it is 0.96. And mercury it is 13.6. And soil it is 2.61. Only lacuna here is you need to convert 1 liter crude oil into a perfect volume. So which is 1000 cc and 1000 10 power minus 6 is meter cube. If you know that, it will be easy for you if you remember the equations. Next one, find out the viscosity when shear stress is so and so and d by dy is so and so. So straightforward. So he has given shear stress. Shear stress is 0.025 kg force per meter square, and d by dy is 0.3 per second. So we have the Newton's equation of viscosity, which is tau is equal to mu into d by dy, and mu is equal to tau by dy. So we have shear stress is here 0.025. So 0.025 divided by 0.3. So d by dy, see here, so it is 1 by second unit for dy, and shear stress is kg force per meter square. So the dynamic viscosity is equal to the shear stress divided by the rate of shear strain. So this is 0.025 by 0.3. So the answer is 0.083 kg force seconds per meter square. So the units are very, very important. So you need to do the problem perfectly only if you have an idea of units and also equations. So free mechanics is very simple, provided you know the simple equations and conversion of units and simple fundamentals, etc. And the other problem, yesterday I have given, the solution is it is bulk modulus. So bulk modulus is, as you know, it is a measure of change of volume when a substance is subjected to pressure. Measure of change of volume when a substance is subjected to pressure. P1 minus P2, that is a pressure change. So when there is a pressure increase, there will be a decrease in volume. So even the problem, if you see here, when there is a pressure decrease, when there is a pressure decrease, when pressure increase, there is a volume decrease here, 0.2%. So the pressure increase is P1 may be some value and P2 may be some value. The increase in pressure is 40 kg per centimeter square. This is the change of pressure. And the volume decreases by 0.2%. So the equation for bulk modulus, we have discussed yesterday, it is minus dP by dV by B. So why the sign is negative? Because there is a reduction volume with increase in pressure, there is a reduction volume. With increase in pressure, there is a reduction volume. So to give a positive value to the K, a negative sign is introduced in the equation itself. So K is equal to 40 kg per centimeter square, that divided by 0.2. 0.2 means not in percentage, you need to take 0.2 by 100. So 40 divided by 0.2 by 100. So the answer is 20,000. So if you take it in kg force, because this is kg per centimeter square, so 40 divided by 0.2 by 100, it is 20,000 kg force per square centimeters. Kg force per square centimeters is bulk modulus. And the surface tension for water droplet is 4 sigma by d. This is the pressure inside, and this is 4. This is sigma, surface tension. So P is equal to 4 sigma by d for water or hollow bubble. Water droplet, and hollow bubble or soap bubble. P is equal to 8 sigma by d. 8 is a constant, and sigma is the surface tension. D is the diameter here, and liquid jet, the equation is 2 sigma. 2 into surface tension by d. This is very, very important for object drive. So when you go for gate question answers, you require, it is required to remember these 3 equations prominently. Yeah. So this is the problem on surface tension. This is for water. So problem is surface tension has given at 20 degrees centigrade, which is equal to 0.0073 kg force, 0.0073 kg force per meter, and the pressure inside is 0.0015 kg per centimeter square. Determine the diameter. So it is very simple. So the equation is, it is required to take the equation P is equal to 4 sigma by d. Students sometimes they are confusing with the equation of the surface tension for water, for soap, and for liquid jet. You try to be remember very clearly. When it is a water, it is 4 sigma by d. When it is soap bubble, it is 8 sigma by d. When it is liquid jet, it is 2 sigma by d. Try to remember that, and you need to derive all these things within a short time. It takes a lot of time, and your time will be wasted in writing the questions in the examination. If you start deriving the simple equations also, try to remember. Your success depends on memory, your sharpness, and getting the right answer from our sharp mind at the appropriate time. That is success for any competitive examination. All are very good, but only focus. If you have more and more focus, and definitely your mind will be very active, and you can memorize. You can have a very good memory, And some students may think that I have less memory, I am unable to, remember the equations. That is not like that. All minds are good, all are active, and only thing is you need to do exercise for the mind. You need to give exercise for the mind. If you are unable to remember in one step, take a paper on that and write the equations. Write the equations. No doubt, within 3 days you will remember all the equations. All the equations. It is easy. It is easy. Don't think that it's a big equation. It is very difficult for me to remember. No, not like that. Not like that. Every mind is a sharp mind. Provided you need to give exercise to your mind. Give exercise to more and more exercise to the mind, like your body. If you give more and more exercise to your body, the body will be active. Similarly, give exercise to your brain, so the brain will be active. So don't think that I am a little weak in remembering the equations. It's not like that. Your mind is sharp enough, your mind is good enough, your mind can remember any equation. Be confident, and your confidence will make you to be perfect and to be successful man. Okay, so the surface tension here at 20 degrees centigrade is only thing here is the equation for this is 4 sigma by T. So it has given surface tension is sigma. So 4 into sigma, so 4 into 0.0073. And one thing, if you see here, this P, pressure is in kg per centimeter square, and this is kg force per meter. So convert to either this in meter square or this in centimeters. Okay, if you convert in centimeters, 0.0073 10 power minus 2, that is force 4 into, the equation is D is equal to 4 sigma by P, or P is equal to 4 sigma by D, because he has to find out D. So D is equal to 4 sigma by P. So 4 into sigma 0.0073 10 power minus 2 by P is pressure is 0.0015. So the equation is 194 centimeters. So you can easily get the solution provided you know the equation and conversion of units from one system to other system. The other problem I am giving solution. This is on capillarity. So more or less all the questions are related to this. This theoretical background. I will get confidence when you exactly discuss the question and answers of objective questions. So the contact angle theta for glass and water is 0. So the the capillarity, as you know, capillarity is due to both cohesion and adhesion. Try to remember that. Surface tension is due to cohesion, whereas the capillarity is due to both cohesion and adhesion. So the contact angle theta for glass and water is 0, and for mercury 130 degrees. So try to remember that he will not give in solution that the contact angle is 0 for glass and water. For example, see here, he has not given, it is glass and water. I have not given the complete details here. It is water. So for water, we can straight away take theta is equal to 0. So when the contact angle is 0, this cos theta, cos 0 is 1. So the equation will be H is equal to 4 sigma by W and D. So if it is a water, this is H is equal to 4 sigma by W D. W is the specific weight here, specific weight of the fluid. If it is a water, we can take a specific weight of water. If it is a specific gravity of the fluid is 0.9, specific gravity of the fluid is 0.9, then specific weight of fluid is 0.9 into 1000. So because the specific gravity of the fluid is the specific weight of the fluid by specific weight of water. Specific gravity of the fluid is specific weight of fluid by specific weight of water. So the specific weight of fluid is equal to specific gravity of the fluid multiplied by specific weight of water. So W1 is the specific weight of fluid, which is equal to specific weight of water into specific gravity. So if the specific gravity is 0.9 into 1000, it will be specific weight of the fluid. So it will be 900. So this is, if it is a water, you can take 1000 kg force per meter cube. In SS system, the specific weight of water is 98 Newton per meter cube, or 9.81 kilonewton per meter cube, and MK system 1000 kg force per meter cube. And so you can take now this cos 0 is 1 here. So this is capital rise. So the capital rise he has given 0.5 mm. So capital rise 0.5 mm. So you can convert 0.5 mm into meters. So 0.5 into 10 power minus 3. 0.5 into 10 power minus 3. So 1 meter is 100 centimeters and 1 meter is equal to 1000 mm. These are very simple. and 0.5 to 10 power minus 3 meters. So that is the capital rise. And 4 into sigma. Sigma is 0.00725 kg per meter. So H is equal to 4 sigma by WD, and W is kg force, 1000 kg force per meter cube. So this H value is 0.5 to 10 power minus 3, and this sigma value is 0.00725, and this cos theta is 1, and this W1 is 1000. So you can find out the diameter here. So if you found out the diameter, it is 0.058 meters or 5.8 centimeters. Very simple, very simple. Yeah, then we'll go to the objective questions. Yeah. First question is a perfect fluid. That means ideal fluid. In the brackets, he has also given ideal fluid. So perfect fluid means it is not natural fluid. So sometimes because for understanding purpose also I have given ideal fluid. Sometimes he will give a perfect fluid is only. Perfect fluid means it is a theoretical fluid. It is a theoretical fluid. So for the ideal fluid, if you remember the discussion, what I have mentioned, all the properties are neglected for ideal fluid. All the properties are neglected for the ideal fluid. So when the properties are neglected, there will be no surface tension. So there will be it is incompressible. All these things, all the properties are neglected. No viscosity, and it is incompressible. Suppose if you see all the answers, real fluid. Sometimes if it doesn't mention also known as ideal fluid, the student may answer perfect fluid may be real fluid. Perfect means maybe real fluid. Perfect means it is a theory. A perfect gentleman. So he's a gentleman with good qualities, which are very, very difficult for any human person. That's why you can use a perfect. Perfect means it is 100% perfect in all the areas which is not existing in nature. So that's why perfect fluid is perfect fluid is ideal fluid. Perfect fluid means it is ideal fluid. So ideal fluid, the answer here is incompressible and frictionless. It is not compressible and frictionless, no friction. Suppose when the ideal fluid is set in motion, no resistance is offered in the opposite direction, as there is no friction, as there is no viscosity, etc. So 1.1, the answer is D, incompressible and frictionless. So today I will complete this chapter. I will submit my PPTs, both the discussion and the objective questions straight away to the organizer, so that they will place that in the location, so that you can have the information with you. But remember the answers. I am giving the answers because suppose if I bold this answer, so straight away think that this is this answer. So okay, it is correct. But you will not confuse with this. The answers will be like that. Suppose he tries to confuse you. That is a particular in gate examinations. So that's why I have not given answers in this. I am discussing the question and giving answers orally for the advantage of for getting the clarity of the question to the student. So the second one is 1.2. When a shear stress is applied to a substance, it is found to resist by static deformation. It is clearly mentioned that the deformation, there will be resistance. There will be resistance by static deformation. We have discussed about the solid and fluid earlier. Solid has finite deformation and the fluid has infinite deformation. Solid has a finite deformation and fluid has infinite deformation. So solid means it has finite deformation. When shear stress is applied to the solid, as a whole it will move so that it has a finite deformation. Whereas the fluid has infinite deformation. Resisted by static deformation is a finite deformation. So the answer for 1.2 is B, solid. Then 1.3, when subjected to shear force, a fluid, what happens? Suppose it is a fluid. The fundamental definition of the fluid is the fluid is substance which is capable of flowing. And when shear stress is applied, what happens to the fluid? This question is a fundamental definition based on the fundamental definition of the fluid. Fundamental definition of the fluid. When subjected to shear force, when shear force is applied, what happens to the fluid? It will have a continuous deformation. Deforms continuously. If we see here the answers, deforms continuously, undergoes static means static is not correct. Static means limited, continuously. So underscore static means it is a limited deformation, which is absolutely wrong. And deforms continuously only for large shear forces. And how small the shear stress may be, only for small shear stresses. Confusing, the answer is confusing. So no doubt it deforms continuously. Generally what happens is we are in a hurry and will yes, it deforms continuously with shear forces. It is force. So F is a typing mistake here. This is a force. So deforms continuously only for large shear force, you may think, or deforms continuously only for a small shear force, you may think, but deforms continuously no matter how small the shear stress may be. Whatever the shear stress, whatever the small value of shear stress, the water flows continuously, the fluid flows continuously. That is answer. So 1.3 is A. You may think that the answer is correct B and answer is correct D also. C is absolutely wrong. But whatever the magnitude of the shear stress, so whether it's a large or small, he mentioned that only means it will not work out for a small shear force. Not correct. Also mentioned only here. Only means it will not work out for large shear stress. Not correct. But seems to be correct. But with the only here, this is wrong. So the A is deforms continuously no matter how small the shear stress may be. That means again this is the fundamental definition. What we have discussed yesterday is a fluid substance is capable of flowing, and with the application of shear stress we have a continuous deformation. That is this answer is from the fundamental definition. Yeah. The one point the answer is small a. 1.4. The conditions of no slip at rigid boundaries. So we have discussed the no slip condition. We have discussed the two parallel plates. If you remember, we have discussed the two parallel plates. Yeah. So if you remember the discussion, we have discussed the two parallel plates. Both are. So this is rigid plate. He has mentioned rigid plate. So this is the stage. This is rigid plate, and this is the plate which is moving. The plate is moving here. This is a rigid plate here. We have only discussion here, not here. So this is a station plate, and we have the fluid here. So fluid inside two plates here. So what happens? The fluid we have adhesive property, viscosity. On account of viscosity, the fluid has adhesion. Adhesion is molecular attraction of liquid to the molecular attraction of solid. So as there is an attraction, as there is adhesion in view of viscosity, the fluid adheres to the bottom plate. So the stationary plate is having zero velocity, and the fluid here, it is also having a zero velocity as the plate is not moving. In other words, the fluid on the plate, close to the plate, and the stationary plate has no relative motion. So the velocity is plate is zero, velocity of fluid is zero here. As there is no relative motion between the fluid on the plate and the stationary solid plate, it is no slip condition. We have discussed that in the earlier discussion. So this is for the real fluid, not for the theoretical fluid. So if it is the theoretical fluid, that is entirely different. Real fluid. So it goes continuously. It moves only with the application of shear force. It moves only with the application of shear force, and there is resistance is often in the opposite direction. This is all for discussions for real fluid. Yeah. So 1.4. The condition of no slip at rigid boundaries is applicable to flow of return fluid. Return fluid is what is return fluid? Return fluid is a fluid which obeys Newton's equation of viscosity. That is different. Ideal fluid cannot be. And non-returning fluid. So flow of all non-Newtonian fluid means there is a non-linear variation between the shear stress and rate of deformation. So only answer here is flow of all real fluids. C. The no slip condition at rigid boundary. So at rigid boundary means this is not moving, the fluid is not moving. And the fluid on account of viscosity, adheres. So because the real fluid is having viscosity property, the answer for this is 1.4 C. So the no slip condition valid for real fluids. Yeah, 1.5. So 1.5 is, if you see, observe here, Newton law of viscosity for fluid statics. Newton law of viscosity for a fluid states that the shear stress is, what is Newton's equation of viscosity? Newton's equation of viscosity is tau is equal to dynamic viscosity into d by dy, or tau is proportional to rate of deformation. So, and there are two assumptions for Newton's equation of viscosity to be valid. So if the Newton's equation of viscosity is taken into account, and it should have two appropriate assumptions. One assumption is, which I discussed yesterday, the distance between the two parallel plates must be small. We have two parallel plates here. One is stationary, other one is moving. And the second assumption is that two plates should be parallel. And the distance between two plates should be small. That is Newton's equation of viscosity assumptions. So he has given proportion to deformation. No. Inversely proportional is absolutely wrong. So because it is only proportional, the shear stress is proportional to deformation. And the answer should be either A or B. But inversely proportional is absolutely wrong. So why the answer is B? So the answer is no doubt it's a B. So it is a proportion to rate of deformation. So d by dy is rate of deformation, not singly deformation. Deformation means a change. It is rate of deformation means d by dy. I mentioned yesterday throughout mentioning rate of deformation. The graph between shear stress and rate of deformation. So Newton's law of viscosity is a proportion to rate of angular deformation. So 1.5 B. Again the viscosity. So viscosity means we have two factors. Fluids means we have liquids and gases. So the behavior of viscosity differs with gases and liquids when the temperature increase or decrease. So if you take viscosity of liquid or viscosity of the gases, you should remember the correct answer. So for gases, it is directly proportional. Viscosity is directly proportional to temperature if it is for the gases. I mentioned that in the discussion. Viscosity is inversely proportional to the liquid. For liquids, viscosity is inversely proportional to temperature if it is liquid. So, for liquids, viscosity decreases. For gases, viscosity increases with the temperature. So, C and D are absolutely wrong. You may be confused with A and B. So liquids, with increase in temperature, viscosity decreases for liquids and viscosity increases for gases. So 1.6, the answer is B. Okay, 1.7. For the fluid, the shear stress was found to be directly proportional to rate of angular deformation. Absolutely correct. Indirectly has given Newton's equation of viscosity. Then the fluid is classified. I told you in the discussion of the graph, when a fluid obeys Newton's equation of viscosity, in other words, when the shear stress is proportional to rate of angular deformation, that is called Newtonian fluid. So don't think about other aspects here. So if the answer is suitable to the question, Immediately tick 1.7a and go to the next question. So 1.7a, Newtonian fluid is a fluid which obeys Newton's equation of viscosity, and linear variation. In other words, the stress is proportional to rate of angular deformation, and you can classify this as a Newtonian fluid when it is a linear variation. So here this is Newtonian fluid. So 1.7 answer is A. Then 1.8 real fluid. Real fluid means practical fluid. So practical fluid which has all the properties, viscosity, surface tension, and it is compressible. So real fluid A. You see here surface tension, correct? And it is incompressible. No, it is compressible also. Zero shear stress, nothing. Constant viscosity and density cannot be constant. You can have any viscosity. So if you see the answer 1.8, all are correctly, misleading you. But a real fluid is a fluid which has viscosity. So because of viscosity only, it offers resistance against the movement of the fluid when it is set in motion in one direction. So real fluid has viscosity, that is the right answer. So 1.8, the answer is D. 1.9. If shear stress tau and shear rate d by the relation of material is plotted with shear, see here, plotted with shear stress and y-axis, du by dy and x-axis. So that is more or less similar graph. So this graph is for this question, but the graph is same. This is also same. So it has taken shear stress on y-axis and shear rate on x-axis. So the behavior of the ideal fluid. So when I mentioned the types of fluids in the yesterday's discussion, whatever may be the shear stress, it will have a continuous deformation. So that is ideal fluid. So ideal fluid is a fluid, whatever the shear stress you apply, you can represent that. Even whatever the stress here, you can represent the positive x-axis as ideal fluid. Yesterday's discussion. So I have written here ideal fluid. So ideal fluid, the answer is 1.9. The answer is B. The positive x-axis. This is the positive x-axis. Suppose if I extend here, in this direction it is a negative. So it is not a negative x-axis. So it is a positive x-axis. So this axis. So that's what we meant. So in the following figure, the line, so the line describes, so suppose here, line describes the rheological behavior of fluid, and the fluid can be classified as. So no doubt this is the shear stress proportional to rate of shear, but it is a non-linear variation. It is a non-linear variation. So when the variation is non-linear, what is the answer? Yesterday, while during discussion, I mentioned that when there is a linear variation between shear stress and rate of deformation, in other words, when it obeys Newton's equation of viscosity, Newtonian. Non-Newtonian means when it doesn't obey Newton's equation of viscosity, it is non-Newtonian. So non-Newtonian means we have a non-linear variation between shear stress and rate of strain. So as there is a non-linear variation, we can straightaway go for non-Newtonian. Don't confuse about all these things. You can straightaway go for, if you are confident about one answer for one particular question, straightaway go to that, the 1.1. And also there is another clue is this. I mentioned the study of fluids, study of non-Newtonian fluids is rheology. Study of non-Newtonian fluids I mentioned in the discussion, in last discussion, study of non-Newtonian fluids is rheology. So rheology means it is non-Newtonian fluid. So you can get a clue from rheological behavior because it relates non-Newtonian. Also you can get a clue that it is a non-linear variation. So from both the clues you can straightaway give non-Newtonian fluid. 1.11. So the next one. The following shear stress, shear rate relationship was obtained for a fluid. So you can draw the graph between tau and shear stress in a simple normal graph, and this is uniform. This is uniform. This is uniform. This is uniform. So it's as it is a uniform variation. So if you draw a graph between shear stress and rate of deformation, so we will get a linear variation. So we will get a linear variation. We get a linear variation. So if the variation is linear, if the variation is linear, 0, 0, it starts from the origin. 0, 0 means it starts from the origin. And if you plot on shear stress and shear rate, the variation is linear. If you have this data, if you use this data, you will be getting a linear variation. So if the variation is linear, if the graph is between shear stress and shear strain, then you can say it is a Newtonian fluid. 1.11, the answer is C. And 1.12. This is the dimension analysis here actually. So the dimension analysis is very, very simple. It is as simple as your 10th and intermediate mathematics. Very simple. There are two systems. One is MLT system. The other system is FLT system. MLT system, FLT system. M represents mass, L represents length. Length means anything. So the unit of meter you can represent L, and T represents time. MLT system. FLT system will come to that for the next question. MLT system. So M is mass, L is length, T is time. MLT is dimension analysis. This is a purely dimension analysis. So any unit, for example, if you are getting a distance, so diameter is distance, so you can non-dimensionalize as M. And this is mass. M is a mass here. For example, mass density is kg mass per meter cube. So then what is dimension analysis here? Mass density is kg mass per meter cube. Kg mass you can take M, and meter cube you can take L cube. So the mass density in dimensional system is M by L3 or ML minus 3. So because the volume is a meter cube, volume is length, and mass is only M. Kg mass per meter cube, kg mass is M, and meter cube is length. So that is M by L cube. So mass density is ML minus 3. Similarly for this, time. For example, acceleration or velocity. So velocity is meters per second. The unit of velocity is meters per second. Then how it will be in dimension analysis? So for meters, it is a length unit. Meters is a length unit. So L, you can take L, meters by second. So second is time. So the velocity is L by T. That means LT minus 1. The answer is LT minus 1. Similarly, acceleration. Acceleration is meters by second square. The unit of acceleration is meters by second square. So meters is a distance unit, L, and second square. Second square is time square. So L by T square is the acceleration in dimensional form. Acceleration in dimensional form, or LT minus 2. Similarly, how will you write for dynamic viscosity? So for that, you need to remember the unit of dynamic viscosity. So the unit of dynamic viscosity in MK system, kg force seconds by meter square. Kg force seconds by meter square. Then how will you use this in MLT system? Because kg force is not M here. So you have to convert kg force into mass. So if you remember Newton's equation of motion, what is Newton's equation of motion? Is equal to F is equal to M into A. F is equal to M into A. So force is equal to, kg force is equal to M into A. What is A? A is acceleration. So we can convert kg force, F is equal to mass into acceleration. We are taking the same kg force, but we are converting into mass for the sake of conversion to MLT system. So the unit is kg force second by meter square, In place of kg force, we'll be using mass into acceleration. So then kg force is equal to mass into acceleration. The mass into mass unit is m, and the acceleration is meters per second square. So m L by t square. M L by t square is for kg force. Then seconds, what is for seconds? So kg force seconds, seconds is t, and meter square is L square. So kg force second by meter square, that becomes kg force is equal to mass into acceleration, that is m into L by t square. Mass into acceleration, mass you can take m, acceleration is L by t square. So ml by t square is kg force, and seconds is t, and meter square is L square. So kg force, meters per second square, L by t square, again t by L square. So the finally it is mass by length unit and time unit, m by lt. So m by lt, so that means m L minus 1 t minus 1. So that is the answer. So 1.12, it is very very important, but normally the students are doing mistakes for writing the unit of dynamic viscosity in MLT system. FLT system they are writing, because F is kg force, and slightly when they take F. I will come to that in the next question. So MLT system. So as the mass is, the unit is kg force seconds per meter square, you need to convert kg force into mass in acceleration. So the mass is m, and the acceleration is meters per second square. So m L by t square, and second is time t by m square is L square. So the finally m by lt, m by lt. So m by lt means again it is confusing. So if you see here m lt, m L minus 1 t has given, but the answer is correct. This is B. M by lt means m L minus 1 t minus 1. So 1.12. The answer is B. Very very important. Every time normally GATE examination is asking such type of question. The other one is 1.13. The dimensions of the quotient of dynamic viscosity FLT system. And earlier is MLT system, now it is FLT system. So the unit of dynamic viscosity is, as you know, we have discussed here, kg force seconds by meter square. Kg force seconds by meter square. So kg force is F, seconds is t, kg force seconds divided by meter square. Meter square is L into L. So it is kg force is F and time is t divided by meter square. Meter square is L square. So that means the equation is Ft by L square. Ft by L square. So Ft by L square is Ft L minus 2. So Ft by L square is Ft L minus 2. So 1.13, the answer is A. 1.13, the answer is A. And 1.14. Typical example of non-Newtonian fluid. Typical example of non-Newtonian fluid of psychoplastic veracity. So what way there are Newtonian fluids? Blood. So the answer is 1.14C. See, blood. Try to remember that non-Newtonian fluid example is blood. Water, air for Newtonian fluid, all these things. So try to remember examples also. For referring non-Newtonian fluid is only blood. So 1.14, the answer is C. 1.15. The kinetic viscosity mu is related to dynamic viscosity mu and density rho. So he has given kinematic viscosity, dynamic viscosity and rho, and the relation he has asking. So the kinematic viscosity is dynamic viscosity mass density. Kinematic viscosity is dynamic viscosity mass density. So you confuse like that. So this is he mentioned mu into rho, mu dynamic viscosity mass density divided by dynamic viscosity, and dynamic viscosity by, this is specific weight, rho into g is specific weight, mass density into specific gravity. Maybe people may be confusing with A and D. So B and C are absolutely wrong. So the kinematic viscosity is mu by rho, and kinematic mu by rho. So relation between mu and rho. So the people may think that maybe this A or D, but this is not mu by W. This is mu by rho. So this is mu by rho. Rho is equal to W by G, not like that. And this is mu by rho. So the answer for 1.15 is J. Then 1.16. A flow of viscous fluid with mu, a flow of viscous fluid with mu is equal to 1.0 Newton second by meter square has a velocity distribution given by u is equal to 0.90 y minus y square. The shear stress at y is equal to 0.045 meters is. So it has given viscosity. Newton seconds per meter square is the viscosity, dynamic viscosity. And the velocity distribution, earlier we have today morning during initial hours we have discussed this type of problem. And velocity distribution given by small u is equal to 0.9 y minus y square. Then what is dE by dy? So the equation is the shear stress is equal to mu into the shear stress is equal to mu into dE by dy. Mu into dE by dy. So dE by dy means 0.9 minus 2y. 0.9 minus 2y. So now the value of y is 0.045 meters. Value of y is 0.045 meters. So dE by dy is 0.9 minus 2y. 0.9 minus 2y. Then if we substitute y value 0.045, so 0.9 minus 2y. 2y is 2 into 0.045. So that is 0.9. So dE by dy is equal to 0. dU by dy is equal to 0. You need not use the equation here. And tau is equal to mu into d by dy. As d by dy is equal to 0, the shear stress is obviously 0. So then you can straight away take C is equal to 0. Not try this 0.9. So cannot be negative or cannot be infinity. Either you can think that it may be 0.9 or 0. Because straight away you are getting d by dy is 0. Need not think about the multiplication. 1 into 0. 1 into 0 is 0. So if it is a 0.9, you may be getting a 0.9. But the answer 1.16 is 0. So this is find out dE by dy. dE by dy is 0.9 minus 2y, where y is 0.045. So 0.9 minus 2 into 0.045. That is also 0.9. So 0.9 minus 0.9 d by dy is 0. So shear stress is mu to d by dy. So as it is 0, d by dy is 0. So the answer is 0. So we will take very short break. It is 9:30. Very short break of 5 minutes time we will take for refreshments. Refreshing you. And today I have the Chief Minister's video conference. I will try to complete this chapter today. And I have to rush to the video conference by the Honorable Chief Minister Garu, along with VC Garu and Minister Garu. But at 3 to 5 minutes gap, 9:30, I will come back at 9:35 and try to complete this chapter. And today I will be completing this fluid properties chapter. And the second chapter, next chapter will start tomorrow. Okay, 5 minutes gap. I will come back at. Yes, my dear student friends, we have completed 1.16. The answer is C, and 1.17. Simple answer. So he has mentioned a perfect gas. Perfect gas. Maybe thinking that perfect fluid does not have viscosity, incomplete, etc. But actually, strictly speaking, a perfect gas does not really exist. So 1.17, the answer is D.